binary decoder 3x8, binary decoder 2x4, 3 tri-state buffers, 8-bit registers, 6 of them, and 4 AND gates. By building the timer circuit, so the timers will generate a repeating wave signal called a clock pulse, which is going to go sequentially from high to low voltage. Its frequency is determined by the value of the resistors and capacitor attached to it. So if I connect a smaller value capacitor, the frequency goes up. The output register clock pulse must have a much higher frequency such that you cannot see the LED blink because the digits on the display light up one by one and we want the user to see the full number on the display. So to briefly explain how the output register works, it's going to take the clock pulse and it's going to feed it into 2 JK flip-flops, which are going to toggle the values from 0 to 3, which are going to be fed into the decoder. So it's going to take 2 bits, the decoder, and it's going to create 4 combinations, and those 4 combinations are going to be fed into the display, essentially picking which digit is going to light up, and the number that's going to be displayed is there because the memory is programmed to give the digit and decimal point by taking the output stored in the register, which is the number and the decimal point. For the control logic, we have an 8-bit shift register with a NOR gate allowing it to shift bits, and that's going to be fed into a memory, which is programmed to create timings so that every clock cycle there's only one timing on, allowing us to split an instruction into steps, and then there's a second memory for more timings, and all the instructions are coming from the instruction register. For the instruction register and the program counter, we just have a 8-bit register and a program counter that are going to be fed onto the bus. They're constantly outputting values, but they're going to be stopped by buffers, which is going to prevent them from outputting values on the bus, so we can control when they're going to be taking values from the bus or outputting values from the bus. Moved on to the ALU, which basically has 2 general purpose registers, A and B, which is going to store 2 different numbers, 8 bits, and these 2 registers are going to be added up in the sum register by adders. So I have 2 4-bit full adders, which are going to be fed into the sum register, and we will decide when the sum register is going to save that value because it has a output enable. This was working by inputting numbers into both registers A and B and checking the sum using LEDs. So I input using ground VCC, and then using LEDs, I check what the output is on the sum register. So for the program memory, we have a register that's going to store the number from the bus, and it's going to be used as an address for the memory right next to it, which is going to be outputting the contents right on the bus. So after that step, I was pretty much done, so it wasn't working at the end, so I had to troubleshoot and figure out what was working and what wasn't. So by testing out every single part, I figured out that the general purpose registers work and that the clock signals work as well. The only thing that seems like it wasn't working is the fact that somehow the value from the program counter is not getting stopped by the buffer and it's getting outputted on the bus probably, and it's bleeding through into the display. So to fix that, I thought it was a noise in the breadboard problem. So to fix that, I tried to add capacitors so put them on specific chips on the pins of the chips and putting them back to ground to reduce noise, so to stabilize the voltage. With the time left, there wasn't much I could do, but I obviously double checked every single connection. I also simplified the circuit by using another memory instead of 2 inverter chips, but this didn't work, and unfortunately I can only prove a few parts of my project work.